Okay, in this example, we've got a bar, homogeneous bar of mass m, which is lying at an angle, 60-degree angle with respect to the truck. It's held in place by friction. The driver of the truck then decides to move to the right with an acceleration of a, wants to get out of there as fast as he can, but not so fast that the bar slips. So the key is for us is to find out what's the maximum acceleration that the truck can have and not have the bar slip. Okay, so let's start out then with our usual procedure here of FBD. What forces are acting on the bar? Normal reaction force at NA, normal reaction force at NB, weight force of mg. Let's talk about the friction. Well, if the acceleration, the truck is too large, then the truck's going to effectively pull itself out from underneath B. In other words, B is going to tend to slip to the left relative to the truck. Friction force will oppose that. So the bar slipping to the left, friction force acting to the right. As the bar slides to the left relative to the truck, A will drop down, so the friction force at A must oppose that. Before we get into the equation, let's talk about the angles. Let's say I call 60-degree angle, let's call that a theta. So theta is this angle here. If I draw a line perpendicular to the bar, then this angle here that NB makes relative to the bar is a theta. Draw a line like this, extending out from the bar. The angle relative to the bar for NA is that angle, and then the angle of FA measured perpendicular to the bar is a theta. Okay, so now we're in a position where we can use our Newton-Euler equations to find that acceleration. First equation I'm going to write down is summation of forces Nx. Well, there's just the friction force FB, positive x. I should say what x and y are. X positive to the right, y positive up. NA is pointing to the left, so that's a minus NA, and that's equal to mAgx just by Newton. Second equation is the summation of forces in y. NB positive, FA positive, the weight mg negative, so that's magy. The moment equation, I'm going to choose to write the moment about the center of mass g, and let's see what we got. Let's do NB first. The component of NB, which is perpendicular to the bar, is NB cosine. Its moment arm about g, that's L over 2, and that's in the minus k. The friction force, component of that perpendicular to the bar, is FB sine theta. That component of force has a moment arm of L over 2, and that's plus k. We do the same thing for NA. Its component perpendicular to the bar is NA sine theta. Moment arm of L over 2, and that's in the plus k. Friction force FA, its component perpendicular to the bar is cosine theta times FA. Moment arm of L over 2, and that's a plus. And we know from the Newton-Euler equation that's the mass moment inertia about g times alpha for the bar. So these equations, these three equations are valid regardless of what's going on here. As long as the bar remains in contact with A and B, and we have friction between the truck and the bar, those equations are valid. What we want to know is what is it about the problem that tells us what we want to know. What we haven't told the problem yet is that we're looking for just the maximum A. Too large of an A, it slips. Less than that, equal to that, G moves along a straight line like this. So AGY is a 0. No rotation of the bar, alpha is a 0. And therefore the x component of acceleration G is the same as the truck. Also, in addition, that for impending slip, the friction force at A is equal to mu sub s times NA. I'll just write that as mu. And the friction force at B is the coefficient of friction times NB. It has to slip at both places or the bar doesn't move. So it's got to slip at both A and B. Okay, so the thinking part is done. We've got our FBD, we have our little kinematics equations that we have, and we say we need impending slip. Unfortunately, the hard part is just getting a solution. It's the algebra that's involved. If I take equation 1, put in the kinematics, I get that mu NB minus NA is equal to MA. Second equation, the y component of the force, says that NB plus mu NA is equal to mg. So these two equations, involving NA and NB, they're coupled together. So what I'm going to do is solve for these to get NA and NB in terms of A. I think basically what I did here was I multiplied the first equation by mu, added it to the second equation, which gave an equation here for NB. The equation is equal to m, the mass, times the ratio of G plus mu A divided by 1 plus mu squared. And then taking that result and substituting back in the first equation gives me NA is equal to the mass times the fraction of mu G minus A divided by 1 plus mu squared, like that. So these are the two expressions we need for NA and NB in terms of A. Put those into equation 3. Well, not yet. What I'm going to do for equation 3 is put my NBs on the same side and set F equal to mu n. So this is NB L over 2 cosine theta minus mu NB L over 2 sine theta. And then all my NA terms on the right side gives me NA L over 2 sine theta plus mu NA L over 2 cosine. Simplifies just a tad. The length of the bar doesn't make any difference. The L's will cancel out. Group together my NB's and get cosine theta minus mu sine theta times NB. The right side you see here is equal to sine theta plus mu cosine theta NA, like that. And if I take the ratio of NB to NA, just from that equation, I get the ratio of sine theta plus mu cosine divided by cosine theta minus mu sine theta. So that comes straight from there. From these two equations here, if I take the ratio of NB over NA, what I get is G plus mu A divided by mu G minus A. So here is the equation we need. Had to do a little bit of algebra to get to that point, but if we substitute in 60 degrees for the angle, we put in the appropriate value there for mu, we have an expression for A. Let's look back to see what we did. Basically, draw the FBD. Friction forces were the most thought-provoking of the five. Friction force opposes the motion. B will slip relative to the truck to the right. Friction force at B is to the right. The bar will tend to slip down, so the impending motion of A is down, friction force of FA is up. We write down our force equations, X and Y, a moment equation about G, and we say, well, what we're looking for is for it to not slip. So not slip, AGY is a 0, alpha is a 0, AGX is A, but for impending slip, FA and FB are equal to mu times NA in NB. And from that point on, it's just solving. First two equations got relationships between NA and NB and A. Took the moment equation, substituted, or found the ratio of NB to NA, and then took our force equation ratio, and that gave us our single equation to find for A.